Okay, that's class content. Let's think about chemistry of biological molecules. Here's the periodic table, and we've simplified it dramatically, only showing you the elements that we care about for this class. And the only reason to show this to you is to point out that biological molecules are really simple. They're principally composed of carbon, nitrogen and oxygen, as well as a lot of hydrogens. We'll refer to these frequently as protons. That makes up the bulk, and a little bit of sulfur, as we'll see. That makes up the bulk of biological molecules. Very simple. In addition, though, we'll also talk about some other atoms: sodium, magnesium, potassium, calcium. These form positively charged ions that are going to be really important. Uh, Interestingly, this first column of the periodic table uh, form ions with a single charge, single positively charged ions. Magnesium, calcium in the second column, those are divalent cations. They're so-called plus two charge. Back here, we see in this next to the last column, chlorine, iodine, those form negatively charged ions. We'll see this last column, those are the noble gases. They closed shell, not typically forming ions. So those are going to be very important for us. Those ionized states of atoms are going to be very important for us. I'll point out a couple of more that crop up once in a while: iron, copper, and zinc. These are in the transition metals. And what I say here, they have variable oxidation states. Well, what that really means is that their charge states can vary. Sodium's always going to be +1, but iron can be +2, +3, various oxidation states, various charge states, and that can be pretty important, as we shall see. Okay, so again, carbon is the main player, and everything else is there too in lesser quantities. Okay, so here's our crash course in chemistry. So atoms are held together with covalent bonds. Let's think about covalent bonds and what we can learn about the way atoms work from the strength of those bonds. So an important aspect of chemistry is quantification. And how chemists quantify is with something called energy. And we'll use this symbol delta G. That's really the Gibbs free energy. And here you see units, kilocalories per mole. That superscript -1 tells us that this is should actually be in the denominator. So kilocalories per mole, that's our units of energy. That allows us, quantifying energies allows us to compare energies. That's the real value of quantification, is being able to say, well, this compares to this, like such and so. Now, let's focus on covalent bonds for a second. So again, energy is the language of chemistry. Calories are the units of energy. Now let's look at bonds. And the simplest thing for us to look at might be a carbon-carbon bond. So here's our first molecular model, guys. We're taking two atoms of carbon, drawing a line between them and saying they're physically bound together. And a carbon-carbon bond has an energy of X. And for our purposes, the numbers don't actually matter. It's being able to place them on this relative scale that's really important. So these single bonds all have energies somewhere around 100 kilocalories per mole. We see that the energy creeps up with different atoms paired together. This often has to do with how closely those atoms can approach one another. We also see that we can have double bonds. So two carbon atoms can be linked with two lines. That tells us that they're sharing more electrons between them. That's the nature of the covalent bond, is shared electrons. And we can have share yet even more electrons here in this triple bond. And we see that as we do so, right, more electrons, the energy of that bond creeps up, 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 up. Something that I'll point out here is that you'll see this is something called a logarithmic scale. We don't go linearly from 1 to 1,000. We go 1 to 10, that's one jump. 10 to 100, that's one jump. So these are factors of 10. Also, we'll refer to these as orders of magnitude. And what we'll say is that even though the lowest on this scale is maybe 800 kilocalories per mole and the highest is 1100, what we'll say is that all of these covalent bonds, shared electron bonds, are on the same order of magnitude, roughly 100 kcals per mole. Now, since I've been talking about calories, let me back up a little bit and say food calories are actually not the same as a chemical calorie. A food calorie is actually 1 kilocalorie or 1,000 calories. Now, you can look up definitions of calories and you'll see a lot. There's lots of definitions. One definition is the amount of energy required to raise the temperature of 1 gram of water 1 degree centigrade. There's a lot of definitions. We don't necessarily care about them. What I do want to make sure you realize, though, is that roughly speaking, when you look at the calorie content on your box of cereal or whatever food product you're reading about, you need to be aware that what we're talking about is different by 3 orders of magnitude, right? From what we're referring to for chemical calories. Okay, last thing on this slide is there's another kind of interaction in chemistry, and that's a non-covalent bond. So when 2 atoms are interacting with each other but not physically linked, they can come together, they can separate, and we'll talk about a variety of non-covalent interactions. And it turns out that these are really important in keeping biological molecules interacting with each other. So let's say covalent bonds are all tying one biological molecule together, as we'll see. Non-covalent bonds often help different biological molecules interact with one another. Last thing I'll say is that we'll see that the non-covalent interactions between 2 atoms are an order of magnitude different, right? Less than 10 kilocalories per mole versus in the hundreds of kilocalories per mole for covalent interactions. So it's an interesting fact that the non-covalent interactions, though very weak, play very important roles in defining chemical interactions. So let's think about those non-covalent bonds. What allows food molecules to stick together? Here are 3 kinds of interaction that I'll describe to you briefly. Van der Waals contacts, they're called. These are just the physical contact of 2 atoms together. Their electron shells bump into each other and they can form some favorable interactions there. We won't go into what an induced dipole is. If you're interested in that, you can read more about it. But basically, when 2 atoms come into contact, they can form a favorable van der Waals interaction that helps them stick together. There are also charge-charge interactions. You're probably familiar with these. You've heard the term likes attract, likes repel, opposites attract, right? These are also called ionic bonds. So as I mentioned before, sodium forms a positively charged ion, chloride forms a negatively charged ion. Together they form a charge-charge interaction, sodium chloride, right? Now, another thing that we like to do in chemistry is, again, quantify. So here we will say that there's a distance separating our 2 charges. Say we're talking about sodium and chloride. There's some distance that's separating those 2 guys, and they feel a force. They feel an attraction or a repulsion based on that distance. And we can write an equation down, and that's something else that we really love to do in science is formulate mathematical expressions that generalize the behavior of systems. So simply stated, though, this force is proportional to the charge on those 2 particles, but most importantly, it's dependent on this distance r. And it's dependent in an inverse way, right? You see where r is. It's in the denominator. That tells us that the farther apart that they are, the weaker and weaker the distance gets. So this is an inverse relationship. Force is proportional to the inverse of the square of the distance between those guys. Anyway, we can quantify these charge-charge interactions. The bottom line is, though, that this gives us a way to mathematically express how 2 charged particles can interact. That is to say, can form non-covalent interactions that help them stick together or help them repel each other. Another really important kind of non-covalent interaction that we'll see frequently in biological molecules is called a hydrogen bond. And hydrogen bonds form when atoms that might be partially positively charged interact with atoms that are partly negatively charged, and that difference in electronegativity binds those 2 atoms together, again, in a non-covalent way. Usually we're referring here to, because it's a hydrogen bond, we're referring to a proton that's shared between 2 other atoms. So here, let's see what we've got. We've got two OHs. So here I've drawn the OHs. I've drawn an OH without a line between them, but they're still bound together. Here I'm showing you the oxygen donating the hydrogen that it's covalently bound to, so that this hydrogen is now shared between these two oxygens. That is a hydrogen bond. And again, very weak non-covalent interaction, but we'll see that it's very important. Let's talk about water. Water is the biological environment for the most part, and water provides us some nice ways of thinking about the importance of non-covalent interactions and hydrogen bonding in particular. Here's the structure of water. We all know water is H2O. There's an oxygen atom. There's two hydrogen atoms. There's also these things that are less important for us, but they will play a role in hydrogen bonding, called lone pairs. They're not physical linkages to anything yet. They're just electrons that are occupying that space. The nice thing about water, though, is that it can form a bunch of hydrogen bonds. So we've got two protons that we can donate and a hydrogen bond, and then we've got these lone pairs that can accept a hydrogen bond with another atom. So here is an illustration of that. Here's one water molecule, and here's another water molecule. This guy is donating its hydrogen in a hydrogen bond to a lone pair in the other water molecule. So an important aspect of this hydrogen bonding is that it can result in a lot of order forming in a bulk solution, but it's dynamic, right? Remember that this covalent bond is worth a lot more energy than this non-covalent bond, so we can form this and break it, and form it and break it without paying a big penalty, whereas breaking this bond can be very, very difficult or energetically costly. I've shown these, so I might as well mention them. The strength of that bond is also, we can also measure that in terms of the length of that bond. So here's a carbon-hydrogen covalent bond, right? And it is 1 angstrom, which is a very small number, 1 times 10 to the minus 10 meters. And the hydrogen bond is twice as long, right? So the non-covalent interaction is a weaker interaction. Now let's consider how these non-covalent interactions can affect the physical properties of a system, like water, for example. Here is a nice Wikimedia cartoon of water and all of its hydrogen bonds. So here you see again the two protons interacting with two other water molecules, donating the hydrogens in hydrogen bonds, and here we're accepting two hydrogen bonds. Water and hydrogen sulfide are very similar in a lot of ways. Oxygen and sulfur come from the same column in the periodic table. They both have these two hydrogen atoms that they bind to, but water boils at 100 degrees centigrade, whereas hydrogen sulfide is a gas at room temperature, boiling at minus 76 degrees centigrade, very cold, even though they have these similar structures. Well, the difference is in the ability of water to form all of these very strong hydrogen bonds. And the sulfur in hydrogen sulfide just isn't able to form as strong a set of hydrogen bonds. And so it doesn't hold together as a liquid phase as readily as water does. So water, those hydrogen bonds keep the water in a liquid phase at much, much higher temperatures. Ethanol is another interesting example. Here we see that its boiling point is 25 degrees centigrade. That's about room temperature to you and me in terms of Fahrenheit. It can form some hydrogen bonds as well, but nothing like the array of hydrogen bonds that water is able to form. So it boils at a much lower temperature. Okay, so physical properties really depend on these non-covalent, weak but plentiful interactions. Let's look at some other little pictures here that are kind of nice to look at. So you've probably all heard that water can form a variety of crystalline structures, ice, frozen structures. Ice IH here is the typical ice structure that we're familiar with. This hexagonal structure, think of snowflakes and their six-pointed stars. This is a plot of temperature versus pressure. And so you can imagine that depending what the phase of water, is it solid, liquid, or gas, the phase is going to depend on both the temperature and the pressure of the system. So at high temperatures but lower pressures, we have liquid water. As the temperature starts to drop, and then here again is a different temperature scale, Kelvin, Here around 270, that's 0 degrees centigrade, 32 degrees Fahrenheit, freezing to our minds, right? And so we see that as we drop the temperature, we go to a solid ice, and this is our, again, our familiar formation. But the hydrogen bond network can shift and change depending on the pressure that we apply. And I won't show you any pictures of these, but you can see that all the different domains of this plot are telling us at what temperature and pressures the ice actually reorganizes so that we can adopt a different crystal structure. Another interesting thing here is here's a crystal structure of this IH ice form, and what we see is this, again, this interesting, here's all of our individual water molecules. We see this hexagonal regular array, and what happens when we freeze water is that these shifting hydrogen bonds that we form in liquid water now lock into place in a single unique configuration. And that's part of the reason that that's part of the reason that water expands when it freezes, right? We're very flexible and free, malleable system here, very rigid, locked, and less dense arrangement here. And so ice actually expands upon freezing. Let's think more about, let's go to this YouTube video. Let's think more about the structure of water. Here's a video of a molecular dynamics simulation of water. And you can see that the water molecules are jiggling around with each other. So here in the middle of the frame is a water molecule, purple oxygen, blue hydrogens. This is slowed down probably 1 billion fold, so we're really probably looking at a few nanoseconds of time here. And now what we've done is shift to show the changing arrangements of hydrogen bonds. So those yellow lines are forming and breaking hydrogen bonds in liquid water. Isn't that beautiful? Let's go back. Okay, so dynamic arrangement of hydrogen bonds, very important for the physical properties of a system.